Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is 9.3, and 9.3 is the integral test. And P-series. That's how you spell P-series. There we go. Alright, so now, here's a theorem. And this is for the integral test. And what we're talking about here is we're saying the integral test for the convergence or divergence of a series. All right. So let's say that we have, so if f is positive and continuous, so not just positive, continuous, and decreasing for x being greater than or equal to 1, and a sub n is equal to f of n, right? So in other words, we're saying this function f of a real variable, it coincides with our sequence a sub n for all the natural numbers. Then, if I know what the series, so let me do it this way. The series of a sub n and the integral from 1 to infinity of f of x dx both converge or diverge. So what we're saying there is that they both behave the same way, all right? So if you can figure out what one of them is doing, you can figure out what the other one is doing. Oh man, spelling is hard. Converge. There we go. So if we can figure out what one of them is doing, you can figure out what the other one is doing. All right. So if we can figure out what the integral is doing, then we can figure out what this series is doing. So for example, let's start with a sub n being equal to 1 over n, right? And I want to know, let's meet. If that's my sequence, what I want to know is, does the series of a sub n converge or diverge? All right. So what we're asking here is, well, what is the series from n equals 1 to infinity of 1 over n doing? Well, what we can do is we can say, well, consider the integral of 1 over x from 1 to infinity dx, right? But in here we know this is an improper integral, so we would say now that this becomes the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. And well, what does this become? Well, the integral of 1 over x is ln of x. So what I get now is the limit as b goes to infinity of ln of the absolute value of x, evaluated from 1 to b. Plugging in our bounds, I end up with limit as b goes to infinity, and that's an infinity symbol. There we go. Of ln of the absolute value of b minus ln of the absolute value of 1. And then at that point we say, well, ln of 1 is 0. And as b goes to infinity, ln goes to infinity. So this tells us now that the integral from 1 to infinity of 1 over x dx diverges, right? It does not converge. It goes to infinity. Well, that now tells us, so that implies that the series from n equals 1 to infinity of 1 over n dn, but no, just 1 over n, sorry. The series from 1 to infinity of 1 over n diverges. And we would say by the integral test. All right. In here, notice that I'm saying that the series diverges, and I'm saying why it diverged. because I did the integral test, and the integral test told me that this diverged. Throughout the next couple of sections, we're going to be discussing different tests for convergence and divergence of different series. And whenever you get a solution, whether you say converge or diverge, you have to, excuse me, you have to explain why. You have to say what test did you use to find that. All right, so B, let's do another one. So let's say I had the series from n equals 1 to infinity of 2 over 3n plus 5. Well, in here, I'm going to say, well, let's consider the integral from 1 to infinity of 2 over 3x plus 5 dx. And we have this infinity there, so we know that we don't like the improper integrals to include that. So I'm going to take the limit as b goes to infinity of the integral from 1 to b of 2 over 3x plus 5 dx. Now let's look at that integral by itself, without the bounds. So if I just look at the integral of 2 over 3x plus 5 dx, well, how would we do this? We would say, well, we got to make a use of u is equal to 3x plus 5. Therefore, du is equal to 3 dx, which tells us that dx is equal to du over 3. Making this integral now the integral of 2 over u. Instead of dx, I've got du over 3. So I get 2/3 ln of the absolute value of u plus c, right, because it's an indefinite integral right now. And that gives us 2/3 ln of the absolute value of 3x plus 5. But that's just that integral. Let's plug in our bounds now. So what we get now is the limit as b goes to infinity of 2/3 of ln of absolute value of 3x plus 5 evaluated from 1 to b. So that gives us now the limit as b goes to infinity of 2/3 ln of absolute value of 3b plus 5 minus 2/3 ln of the absolute value of plug in 1. 3 times 1 is 3 plus 5 is 8. ln of 8. Right? And as b goes to infinity, well, it doesn't really matter what this part over here is doing. This right here goes to infinity. So if we have infinity minus a specific number, which gives us infinity, so we again get that it diverges. So what does that tell us? What we found is that the integral from 1 to infinity of 2 over 3x plus 5 dx diverges, which implies now that the series from n goes to 1 to infinity of 2 over 3n plus 5 diverges by the integral test. Right? C. The next one, C. Let's say I had the series from 1 to infinity of 1 over n squared plus 1. Alright? And again, we're trying to see what this does. Well, I'm going to take the integral. Alright, I'm going to say we have the integral from 1 to infinity of 1 over x squared plus 1 dx. Right? So, what does that do for us? Well, we're going to say now, the integral of 1 over x squared plus 1. Actually, hold on. We have an improper integral. Improper integral. We cannot continue unless we change that. So the limit as b goes to infinity of the integral from 1 to b of 1 over x squared plus 1 dx. And what does that give us? Well, the integral of 1 over x squared plus 1 is arctan. So I have the limit as b goes to infinity of arctan of x, evaluated from 1 to b. So plug in our bounds. Limit as b goes to infinity of arctan of b minus arctan of 1. But now, arctan of 1. Arctan of 1 is pi over 4. As b goes to infinity, what does arctan go to? Well, first let me remind you of what arctan looks like. This is what arctan looks like. where this right here is negative pi over 2, and this value up here is pi over 2. So as b goes to infinity, arctan goes to pi over 2. So what we get now is, well, pi over 2 minus pi over 4, which is pi over 4. So what do we find here? What we found here is that the integral from 1 to infinity of 1 over x squared plus 1 dx is equal to pi over 4, so it converges. So the fact that our integral converges, this tells us now that our series from n equals 1 to infinity of 1 over n squared plus 1 converges by the integral test. Now, before I continue here, I want to make an important distinction here. The integral converges. The series converges. Good. The integral converges to pi over 4. The series, nope, we can't say anything about that. We can't say what the series is converging to. All this is telling us is that it also converges. It's not telling us that it also converges to pi over 4. It's not saying that. All right, the integral test just tells us that, well, if the integral converges, then the series converge. If the integral diverges, then the series diverges. But not what it might converge to, just that it does converge. All right. Um, so now, I want to talk about a theorem here. So theorem. This is the convergence of P series. And first, let's talk about what a P series is. So a P series is in the form of the summation from 1 to infinity of 1 over n to the p. All right. In other words, this is 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus so on and so forth. All right. This series, if you have it in that format, it converges for p being greater than 1 and diverges for p being between 0 and 1, including 1. All right. And I'll make a note here. If p is equal to 1, then we get the series from n equals 1 to infinity of 1 over n. And if you recall from example A, that diverged. All right. So that diverges. This series is called the harmonic series. That series, the series is called the harmonic series. And the harmonic series is a very important series because the harmonic series is the most common example of the following. In here, our sequence a sub n being 1 over n, if I take the limit as n goes to infinity of 1 over n, that goes to 0, right? So our sequence goes to 0. But our series of 1 over n diverges. All right. If you recall from chapter 9.2 from this previous section, we spoke about the test for the nth term test for divergence, right? And that one said that if the sequence did not go to 0, then the series diverges, right? Prior to that, the statement was if the series converges, then the sequence goes to 0. This is a prime example of a sequence going to 0, but this series being diverging. It's a divergent series. So now we know that the harmonic series is a divergent series because of the integral test, and the integral test brought about this P series, the convergence of P series. All right, so now that allows us to do some quick examples. So if I have, for example, the series from 1 to infinity of 1 over n to the fifth, Well, if I'm asking whether it converges or diverges, I know right away that it converges because it's a p-series in general, right? And here our p being 5, and 5 is greater than 1, so it converges. If I had the series from n equals 1 to infinity of 1 over, let's say, n to the 5/9, all right, this diverges. And again, because of p series, all right, 5/9, that's our p is 5/9, and 5/9 is between 0 and 1, so therefore it must diverge, right? So that's a great thing about p series. It allows us to look at some of those quite quickly. But let's do some other examples because we are talking about the integral test here. So let's say I had the series from 1 to infinity of arctan of n over n squared plus 1. Well, in here, what we're going to do is I'm going to take the integral. So I'm going to say, let's look at the integral from 1 to infinity of arctan of x over x squared plus 1 dx. All right. And in here, what we're saying is we'll need the limit as b goes to infinity from the integral from 1 to infinity of arctan of x over x squared plus 1 dx. And let's look at just that integral itself without the bounds. So the integral of arctan over x squared plus 1 dx. And how do we do this integral? Well, what we say is let the numerator arctan be our u. And then our du would be 1 over x squared plus 1 dx, right? Because that's the derivative of arctan. So from here, what this tells us now is that we get the integral of u du, right? Because that's dx over x squared plus 1, dx x squared plus 1. That's our du. And then that arctan was just our u. So this gives me u squared over 2, right? Plus c. But u was arctan, right? So here I end up with arctan of x squared over 2 plus c. But that was without the bounds. So now let's look at the integral with the bounds. So now I'm going to have the limit from b goes to, as b goes to infinity, of arctan of b, excuse me, arctan of x squared over 2 evaluated from 1 to b. And now plugging in our bounds, we end up with the limit as b goes to infinity of arctan of b squared over 2 minus arctan of 1 squared over 2. And at that point, we say, well, we already know what happens as b goes to infinity with arctan, right? That goes to pi over 2. So I have pi over 2 squared over 2 minus arctan of 1. We already know what that is also. That's pi over 4. So I have pi over 4 squared over 2. At this point, what does that give me? That gives me, well, pi squared over 4, and then that over 2, minus pi squared over 16, and then that over 2. So common denominator, well, let's actually reduce this a little bit. We've got pi squared over 8 minus pi squared over 32, right? What I'm doing there is, instead of dividing by 2, I'm multiplying the whole thing by 1/2. And that's how I get those values. And at that point, we say, well, what's the common denominator? The common denominator is 32. The second numerator there is already over 32, so just copy it. The first one, well, to go from 8 to 32, multiply by 4, so I get 4 pi squared. And at that point, 4 pi squared minus pi squared is 3 pi squared over 32. And, well, what is that? That's an actual value. That is an actual value, which tells us that our integral converges, right? It's a convergent integral. There we go. So that now tells us that, so hold on, so let's see what we found. We found that the integral from 1 to infinity of arctan of x over x squared plus 1 dx was 3 pi squared over 32, which implied convergent. That implies that the series from n equals 1 to infinity of arctan of n over n squared plus 1 converges by the integral test. All right, and there you go. Let's do one more. So what was this one? F. So G. Let's say I had the series from n equals 1 to infinity of ln of n over n squared, right? And again, I'm going to do the integral test here. So let's see. So it's integral from 1 to infinity of ln of x over x squared dx. And then what do we have to do now? Well, in here, let's see, how are we going to do this? First, that infinity shouldn't be there, right? So we should be writing this as the limit as b goes to infinity of the integral from 1 to b of ln of x over x squared dx. All right. And now what are we going to do? Well, what we're going to do here is integration by parts. All right. Recall that integration by parts is a thing. And with integration by parts, what we need to have, well, first let's recall the formula. The formula was that the integral of u dv is uv minus the integral of v du. So, and along with that came along this acronym, LIATE, L-I-A-T-E. All right, and that again, if you recall, that reminded us how to find out what our u is. So, what is our u, and then what is our dv? Because our dv is going to be everything else except our u, right? So in here, based off of LIATE, our u is the logarithmic, because L is logarithmic. So u is ln of x, which tells me that du is 1 over x dx. Our dv is going to be the rest of the integral. So in other words, 1 over x squared dx. And to find v, I need to integrate that. Well, the integral of 1 over x squared is negative 1 over x. And now, at this point, I get that we get the limit as b goes to infinity of, all right, so uv minus integral of v du. So uv, so that's negative ln of x over x, right? uv minus integral of v, negative 1 over x, du, 1 over x dx. So let's just rewrite that a little bit nicer. We get here the limit as b goes to infinity of negative ln of x over x. Oh, and by the way, what were our bounds? From 1 to b. So this is from 1 to b. This is from 1 to b. From 1 to b. All right, so now this negative can be pulled to the outside, so I have plus the integral of from 1 to b of 1 over x squared. And from there, well, we can go ahead and evaluate. Let's take this integral. So I end up with the limit as b goes to infinity of negative ln of x over x. The integral of 1 over x squared is negative 1 over x. Right? We had already found that out over here. Evaluated from 1 to b. So what does that give us? Well, let's see. We're going to get here, plug in b. So I end up with negative ln of b over b minus 1 over b. And then minus negative ln of 1 over 1 minus 1 over 1, right? And now, let's see what we can do here. Ln of 1 is 0. And then we have minus 1 over 1. So what do we really have here? We have negative ln of b minus 1 over b, right, common denominator. And then minus a negative 1, so that means plus 1. So the last part there was just plus 1. But now, recall, well, let's notice here that I have some bad notation. I forgot to write my limit. But recall that we're finding the limit. right? So because we're finding the limit here, let's see what happens as b goes to infinity. Well, as b goes to infinity, this part right here, the top is over infinity, the bottom is infinity, so I get infinity over infinity, which we know is not good, right? So how do we do this? Well, let's see. What we're going to say now is, let's use L'Hopital's rule. All right, and in here b is a real variable, so we can just go ahead and just take L'Hopital's rule as usual. So I end up with the limit as b goes to infinity of -1 over b. That minus 1 goes away, right? The derivative of the top. And then on the bottom, the derivative of the bottom is just 1, right? We're taking the derivative with respect to b. And technically, we still do have this plus 1 on this outside, right? Because this limit stuff was only for the part that's being affected by b. This 1 is not being affected by b, so it's not being affected by that limit. At that point, we say, well, as b goes to infinity, this goes to 0. So I end up with 0 plus 1, which is just 1. So what do we find here? What we found here is that this integral of ln of x over x squared, so this tells us that the integral from 1 to infinity of ln of x over x squared dx, well, it equaled 1, which implies convergent. And because this integral is convergent, that tells us now that the series from 1 to infinity of ln of n over n squared also converges by the integral test. All right, so 9.3 is a short section. In fact, we are done. That is the end of 9.3. But again, it's just with all of this, it's just integrating and seeing whether or not the integral converges or diverges.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.